There is a standard way to tell the story of the early universe, and it is, in most respects, a good one. We begin at some time close to zero, trace the temperature as it falls from values too large to be written without scientific notation, map the phase transitions as the fundamental forces separate and the particle zoo thins to the species we now catalog. We speak of energy densities and expansion rates, of the Planck epoch and the inflationary era and the epoch of recombination. The numbers are staggering in magnitude. They are presented with appropriate gravity. And then we move on. What we do not tend to discuss, what the standard treatment almost uniformly passes over in silence, is what those numbers mean for the geometry of spacetime itself. Energy density figures are quoted as though they were items on a thermodynamic inventory. Large, yes, unfamiliar, certainly, but fundamentally the same kind of thing as the temperature of a star or the pressure inside a neutron core. They are treated as scalars describing a physical system. They are almost never treated as what they also are, descriptions of a space-time manifold operating under conditions so geometrically extreme that our mathematics begins to break down. This is not a minor omission. It is not a pedagogical choice to simplify for a general audience. It persists through graduate-level treatments, through review articles, through the cosmological texts that line the shelves of theoretical physicists. The FLRW metric and the Friedmann equations are presented with rigor and appropriate caveats. The energy density figures are quoted, and then the geometric consequences of those energy densities, the consequences that general relativity demands by its own construction, are quietly set aside. I want to examine them, not because examining them resolves anything, but because naming what our language cannot adequately represent is itself a form of intellectual honesty that the subject deserves. What the FLRW metric is and what it isn't. The Friedmann-Lemaitre-Robertson-Walker metric is one of the great achievements of applied general relativity. It takes a question that would otherwise be intractable. What does the universe look like as a geometric object? And renders it soluble by an act of principled idealization. The metric assumes that the universe is homogeneous and isotropic on sufficiently large scales. It imposes uniformity. It says, at every point in space, at any given cosmological time, the universe looks the same in every direction as it does from every other point. This is not a description of any particular small region. It is a description of the large-scale structure as a whole. The payoff is significant. From that assumption, Einstein's field equations reduce to the Friedmann equations, clean differential equations relating the expansion rate of the universe to its energy content and curvature. The equations work. They give us the expansion history. They give us the relationship between energy density and the Hubble parameter. They underwrite our predictions about the cosmic microwave background and the large-scale distribution of matter. The framework earns its place, but the homogeneity and isotropy ansatz does not describe what spacetime was locally doing. It cannot. The FLRW metric is a smooth, globally symmetric construction built precisely to suppress local variation. The global curvature parameter K, that single number encoding whether the universe is positively curved, flat, or hyperbolic, describes large-scale topology. It is not a statement about the curvature experienced at any particular location, at any particular moment, in the regime where the energy densities in question were actually operative. This matters enormously because the local geometry is not the global geometry. In a system with extreme energy density, the local curvature of the spacetime manifold follows from the stress energy content at that location. The Einstein field equations are a local statement. The curvature here is determined by what is here. The FLRW framework, by construction, averages over this locality. It gives us the large-scale kinematics without the local geometry. And in the early universe, the local geometry is precisely the thing that most warrants examination. There is nothing dishonest about this in a formal sense. Physicists who work with FLRW know what they are doing and why. The problem is in the communication, in the implicit message sent when energy density numbers are presented without their geometric content. The metric's success at describing the expansion history can create the impression that it has also described the state of the manifold. It has not. It has described the skeleton, the flesh, the actual geometric character of those densities has been left aside. In The Illusion of Reality, we traced how the holographic principle suggests that the boundary description of a region may be more fundamental than its interior, that space as experienced volume might be an emergent description rather than a primitive one. The FLRW metric is an instructive parallel. It is a successful emergent description, one that captures the large-scale behavior of the universe by deliberately suppressing everything happening locally. It works at its level, but it does not tell us what the spacetime manifold was actually doing in the regime that produced it. What the numbers actually mean. Let us take the Planck epoch seriously as a geometric statement. The Planck epoch refers to the period from the beginning of the universe to approximately 10 to the negative 43 power seconds, a unit of time so small it bears no relationship to anything in human experience, and only a formal relationship to anything in experimental physics. During this epoch, the energy density of the universe approaches the Planck density, approximately 5 times 10 to the 96th power kilograms per cubic meter. That number is routinely quoted. It is rarely geometrically interpreted. In general relativity, energy density is not merely a thermodynamic quantity. It is a source term in the Einstein field equations. The stress-energy tensor, of which energy density is a component, appears on one side of those equations, and the curvature of spacetime appears on the other. They are not two separate things that influence each other. They are two descriptions of the same physical reality. The curvature is not a consequence of the energy density in the way that a shadow is a consequence of a light source. The curvature is what the energy density is, expressed in a different language. This means that the Planck density implies a specific geometric fact. At those energy densities, the radius of curvature of the spacetime manifold is on the order of the Planck length, approximately 1.6 times 10 to the negative 35 power meters. In geometric terms, this is the length scale at which spacetime is curved back on itself so tightly that our ordinary conception of smooth spatial geometry ceases to be reliable. It is not that spacetime is curving sharply in the way that space curves near a massive body. It is that the manifold itself is operating at a scale where the concept of smooth geometry approaches its own limits. The consequence worth dwelling on is this: every point in the Planck epoch universe carried curvature comparable to what general relativity predicts at a black hole singularity, not near one, not in the vicinity of one. At one, that regime of curvature where the Ricci scalar diverges, where tidal forces across arbitrarily small separations become formally infinite, where the field equations predict their own breakdown. The difference is that in a black hole, this condition applies to a single point in space. In the Planck epoch, it applied everywhere, simultaneously, distributed across the entire universe. In the fold in space, we introduced the Planck length as the scale at which Kaluza-Klein theory predicts the compactification of additional spatial dimensions, the point at which extra-dimensional structure becomes inaccessible to any instrument built at our scale. That post was concerned with what the Planck length implies for the large-scale topology of space. This post is asking a prior question. The entire early universe was once operating entirely at that scale. The regime in which smooth geometry becomes unreliable, in which extra-dimensional structure may become dynamically significant, in which classical GR predicts its own inadequacy, that was not a feature of some exotic object at the boundary of a singularity. It was the condition of everything. The standard cosmological treatment presents this epoch with its energy density figure and proceeds to the next phase transition. To proceed without pausing on the geometry is to mistake the inventory for the thing itself. The number is not a curiosity. It is a description of a spacetime manifold operating in a regime our mathematics was not built to represent. Inflation's concealed geometry. The inflationary epoch is typically presented as a solution to three observational puzzles: the flatness problem, the horizon problem, and the absence of magnetic monopoles. Inflation, the postulated period of exponential expansion from roughly 10 to the negative 36 power to 10 to the negative 32 power seconds, addresses all three with a single mechanism. The universe expanded so rapidly that its initial curvature was diluted to near zero, Its initially disconnected regions were brought into causal contact before inflation began, and monopoles were diluted to undetectable densities. The solution is tidy. The mechanism, an inflaton field slow rolling down its potential, generates predictions that have been tested against the CMB power spectrum. The framework earns its place, as the Friedmann equations earn theirs. What the inflationary narrative rarely foregrounds is the geometry of the spacetime it describes. The spacetime of inflation is approximately de Sitter space, a maximally symmetric solution to Einstein's field equations with a positive cosmological constant corresponding to a universe dominated by the energy of the inflaton field. De Sitter space is not a gently stretching rubber sheet. It has a horizon structure. It has thermodynamic properties. It has a specific and unusual relationship between the vacuum energy density and the curvature of the manifold. The Hubble parameter during inflation, which sets the rate of expansion, is related to the inflaton energy density through the Friedmann equations. But what those equations are encoding is geometric. The inflaton field is not merely causing the universe to expand. Its energy density is sourcing a curvature of the spacetime manifold that has no analog in any physical environment we have ever directly observed. The phrase that tends to describe inflation, the universe expanding exponentially, maps the process onto the intuition of stretching. Something is getting bigger. But de Sitter space is geometrically specific in ways that stretching cannot capture. It has a cosmological event horizon, structurally analogous in several respects to a black hole horizon. The geometry during inflation, at the energy scales relevant, produces curvature corresponding to densities many orders of magnitude above anything in nuclear or atomic physics. The smooth, graceful exit, the inflaton settling into its minimum, reheating the universe, handing the story back to standard cosmology, describes what happens after the geometric violence. It does not describe the violence itself. In the shadow universe, we traced the matter-antimatter asymmetry of the early universe and used Penrose diagrams to map the causal structure of spacetime, the geometry of what can influence what. The asymmetry that produced our existence emerged from precisely this epoch. But the Penrose diagram, useful as it is for causal reasoning, is also a smooth construction. It represents the large-scale causal structure without representing the local geometric character of the manifold during inflation. The two descriptions are complementary. One shows us the causal skeleton. The other, the one rarely told, would show us the curvature that lived inside it. The rubber sheet metaphor is not false. It captures something real about the expansion. But it is one of those useful approximations that can, by its very usefulness, prevent the more accurate picture from forming. The sheet is smooth. Inflation's geometry is not. Stress energy is geometry. At some point in every physics education, Einstein's field equations are written down, and the statement is made that they relate the geometry of spacetime to its energy content. The compact tensor form is presented, the Einstein tensor on the left and the stress energy tensor on the right, and this is rightly identified as one of the great conceptual achievements of the 20th century. Then the course continues, and the two sides begin to be treated again as separate categories. One the response, one the source, the geometry, and the matter living in their respective conceptual homes. This separation is a convenience that quietly undermines the conceptual content of the theory. The field equations do not say that energy density causes curvature. They say that energy density is curvature, written in a different language. The stress energy tensor is not something that influences the geometry from outside. It is the other face of the same geometric reality. When you quote an energy density, you are making a claim about a spacetime manifold. You are not describing a substance sitting inside a geometric background. You are describing a geometric state. The background and its content are not two things. They are one thing described twice. This identification has physical content. It means that there is no consistent way to describe the energy density of the early universe without simultaneously making claims about the Riemann curvature tensor, the Ricci scalar, the tidal forces operative across any given length scale, and the regime of validity of the smooth manifold assumption itself. These are not separate discussions that can be deferred. They are part of what the energy density figure means. The Riemann curvature tensor is the object that fully encodes how spacetime curves. It governs the relative acceleration of nearby geodesics, what we experience as tidal forces, what tears an infalling body apart near a black hole. In flat spacetime, it vanishes. Near a massive body, it grows. At a black hole singularity, it diverges. In the Planck epoch, every component of the Riemann tensor is operating in the regime where GR predicts its own inadequacy. The tidal forces across Planck scale separations are formally infinite in any classical treatment. The geodesic equation, which describes how objects move through curved spacetime, is operating on a manifold that has lost the properties the equation requires. None of this appears in the temperature-time axis. The energy density is quoted, and we are left to assume that it is a large number without a geometry. It is not. It is a description of a manifold for which we have no adequate language. Saying this does not diminish the achievement of the Friedman framework. It situates it. The right tools for describing the large-scale kinematics of a universe that was locally operating in a geometric regime beyond description. They work, but they work by not looking at what they cannot see. Spacetime foam and the honest frontier. John Wheeler, working from the logic of quantum mechanics applied to general relativity, arrived at the concept of spacetime foam. The argument is straightforward in principle. The uncertainty principle establishes that energy fluctuations on short time scales are not merely possible but mandatory. Apply this to the metric of spacetime itself, and recall that in GR the metric is not a fixed background but a dynamical field. And you find that at length scales approaching the Planck length, those fluctuations become violent enough to destroy the smooth differentiable structure that the manifold is supposed to possess. The topology itself becomes uncertain. Geometry fluctuates. The classical picture of a spacetime that can be differentiated, mapped with coordinates, and integrated over becomes unreliable. Spacetime foam is the honest acknowledgement that our description runs out. It is not a proposed physical substance. It is a statement about the limits of our conceptual architecture. At Planck scales, the smooth manifold that underpins both GR and quantum field theory ceases to be a trustworthy description of anything. We do not know what replaces it. String theory proposes extended objects whose dynamics smooth over singularities. Loop quantum gravity proposes a discrete structure at the Planck scale in which area and volume are quantized. Neither is confirmed. The frontier is genuinely open. What this means for the early universe is stark. Our cosmological models of the Planck epoch are kinematic sketches. The FLRW metric, the Friedman equations, the energy density figures, these describe the symmetries we impose and the expansion history that follows from them. They are not geometric descriptions of the manifold itself in that regime, because we do not have the physics to construct one. The model works as a large-scale account. At the scales where the energy densities are physically operative, where the Riemann tensor is in the regime of breakdown, where the manifold has lost the properties our equations require, we have no model at all. We have inference from after the fact. In the illusion of reality, we trace the holographic principle's implication that the three-dimensional world we inhabit may be an emergent description, that what we call depth may be a consequence of informational structure rather than a fundamental feature of reality. Spacetime foam is the same insight approached from the other direction, not from the large-scale structure of spacetime revealing informational encoding at its boundaries, but from the small-scale structure of spacetime dissolving into something our geometry cannot represent. In both cases, the smooth manifold is not the floor of the well. It is the surface level of a deeper account we have not yet written. The reason cosmology does not dwell on this is not that it has been resolved. The reason is that we genuinely do not have the physics to address it. That is an honest position, and it is the correct one to hold. What is less careful is presenting energy density figures that imply a geometric condition we cannot describe without naming the implication. What we are actually saying when we write that the energy density of the Planck epoch was approximately 5 times 10 to the 96th power kilograms per cubic meter, we are making a geometric claim about a spacetime manifold. We are saying that the Riemann curvature tensor was operating in a regime where classical GR predicts its own breakdown. We are saying that the concept of smooth differentiable geometry, the foundation on which both GR and quantum field theory are built, was not a reliable description of what the manifold was doing. We are saying, in other words, that the early universe was operating in a domain for which we do not yet have a physics. This is not a crisis to be resolved before cosmology can proceed. The Friedmann equations are not wrong. The expansion history is well supported by observation. The temperature-time axis is a legitimate description of a real progression. None of this is undermined.